Midas NFX Lecture 4 Steady State Thermal Problem. And this is a heat sink problem. We built a 3D model of a heat sink and save as a parasolid. So now in Midas NFX we open a new case, give it a name, and import the geometry. So we finish with the first step, opening a case and building a 3D model. The second step would be material, and generally we use aluminum 6061 for heat sink in a computer. So I choose 6061 aluminum alloy, and I'll connect the 3D geometry with the aluminum material. So the property step is to connecting the geometry with the material, and this is the loading of the material. So I have finished with the second step. Third step will be building or generating the meshes. So I choose the volume and I'll accept the default mesh size and implement the meshing process. So I finished with the third step. For the fourth step, first of all, I will heat the bottom surface because I didn't draw the CPU volume. And there's a volume heat source here. You can define a heat source, volume heat source. But now I'm going to define the area heat source because I didn't draw the CPU volume. So I'll define the flux. And since it is 28 watts, so I'll divide it by the area, 2,500 millimeter square. So it is a 0.0112, and this is the number of watts, 28 watts in a area here. So this will be the heat source flux, 0.0102, and the object will be here. I'll choose a surface. This is the heating surface. Okay, actually this is 20 watts totally. Now I'm going to define the constraint or the convection. For the convection, I'll choose surface, and I'll select all the surfaces except for this one. This is a heating surface, right? So I've chosen 156 surfaces, and the ambient temperature I'll define it as 20 or 25, and then the coefficient of convection is 10 watt meter square K, but in this unit is 1 times 10 to the minus 5. 1 times 10 to the minus 5, or it is 10 times 1 over a million. So actually for the other unit, SI unit, you can see that it is 10 watt meter square, right? So it is easier this way. You can choose the unit. Okay, now we are finished with step 4, where we heat the heat sink at the bottom surface, and we define all the 156 surfaces to be convecting, and their ambient temperature will be 20 degrees C, and the convection coefficient is 10 watt per meter square, and it is a stagnant condition, stagnant air, coefficient of convection. So we have finished with step 4, and we have totally described the problem. So we have finished with the preprocessor, and now we can go ahead and perform analysis. Before we perform analysis, we define a problem, define a heat transfer problem, and you can also edit the content of the analysis, since this is a steady state thermal analysis. So I don't have to give it a time or time step or the initial temperature, so I can start the solution phase. And this is the step 5. And step 6 will be the result. And the result, the default result, will be temperature, first of all. And then there will be other default result, such as thermal gradient and flux, heat flux. So what is important for me is the temperature of the heat sink. So I'll probe the temperature here. And temperature is 116 degrees C. And this is the result of the analysis. And steady state is a condition where the system arrive or reach a thermal equilibrium. In other words, heat dissipation and heat source are in balance. So there's no more temperature change. So it is called steady state thermal analysis. And this is lecture 4 for Midas NFX.